Hello students, today I will continue with the first model, that is conduction. In that, the one-dimensional steady-state heat conduction equation without heat generation in Cartesian coordinates will take. In that one, we will consider a slab of thickness L. Then it is subjected to a temperature at T1 at x is equal to 0 and temperature T2 at x is equal to L, and also this slab is sufficiently long along the x and y and z directions so that the only heat transfer takes place along the x direction, and its electrical analogy is taken that one, that is a resistance or that one resistance concept. Okay, between the temperature T1 and T2 the resistance R is the conduction resistance L by Ka is there. Then after consideration we have to take the three-dimensional heat conduction equation in Cartesian coordinates. Already we know that one, that is a dou square T by dou x square plus of dou square T by dou y square plus of dou square T by dou z square plus q by k, that is equal to 1 by alpha dou T by dou T. Then for one-dimensional steady state without internal heat conduction equation, this can be reduced. For one-dimensional heat conduction along the x direction, only the first term remains, the second and third term will be becomes 0. Then steady state, this term dou T by dou T term will be becomes 0, that is the variation of the temperature with respect to time will be 0. Then without internal heat generation, that this term will become 0. Then the equation reduced to that one, d square T by dx square is equal to 0. Then this equation is subjected to boundary conditions. Those boundary conditions are the temperature at the two surfaces, that is at x is equal to 0, T of x is equal to T1, at x is equal to L, T of x is equal to T2. Then the solution for the above equation can be obtained by integrating twice. Okay, this equation if you integrate twice, after the integration of once we are going to get the dt by dx is equal to c1. After again integration, t of x is equal to c1x plus c2 we are going to get, and where c1 and c2 are arbitrary constants. Applying boundary conditions, we can write at x is equal to 0, c2 is equal to t1. If x is equal to 0, if we substitute, c2 is equal to t1 we are going to get. Then at x is equal to L, if you substitute x is equal to L here, that's C1 L plus of C2, already T1 we know that. Then at x is equal to L, T is equal to T2. If you take this one, then C1 T2 is equal to C1L plus T1. Then C1 is equal to T2 minus of T1 by L we are going to get. Then this if you substitute in the equation 3, okay, the T of x whatever is there, if you substitute on that one, C1 and C2, the substituting constants in equation 3 we have, that is T of x is equal to T2 minus T1 by L into x plus of T1. Then the heat flow through the slab of area A is given by, okay, here this is the temperature distribution through the slab. Then the heat flow or a heat transfer across the slab, that can be given by this equation from the Fourier law of conduction. We can write q is equal to minus ka dt by dx at x is equal to 0, and here we can t of x you can substitute and differentiate that one. Otherwise here from this equation, after first integration, dt by dx is equal to c1, the c1 value whatever is that t2 minus t1 by L, that also we can substitute at x is equal to 0, that is c1 that we substituted here, therefore minus ka t2 minus t1 by L, okay, that we are going to get. Then this equation if you rearrange that one, q is equal to k t1 minus t2 by L. Then if you rearrange this equation in terms of the resistance, thermal resistance, the t1 minus t2 by R, R is L by K. The R is called thermal resistance of the slab. This concept is analogous to electrical resistance. Already I told you that one analogous to the electrical resistance. If you consider that one, convection heat transfer also from the either of the surfaces, from the surface at x is equal to 0 and from the surface at x is equal to L whatever is there, for that we are going to get this equation, electrical analogy. And for that electrical analogy, the heat transfer we can write the rate of heat transfer q is equal to h1a t infinity minus of t1, that is equal to k t1 minus t2, then that is equal to AH2 T2 2 minus of T infinity. Then again we can write in terms of the resistances this equation the resistance if you take in the denominator and the numerator temperature differences for all the three terms. And after that, if you add the numerator and denominator, we are going to get this one here, T by infinity 1 minus of T infinity 2. Okay, this internal temperatures, that T1 and here plus and minus, and T2 here minus and plus, both will get cancels, and there we are going to get T infinity 1 minus of T infinity 2 by 1 by AH1 plus of L by K plus of 1 by AH2 we are going to get. Okay, where the R total we can write, and that R total will be the total resistance. And the simple numerical here it is there. Okay, that will not consider here. Later we'll take the numericals. And now we'll take that is one-dimensional steady state heat conduction equation without heat generation through cylinders. Okay, here through the cylinders we are going to find out the whatever the heat conduction equation is there, temperature distribution as well as the heat conduction equation we have to derive from this one. Okay, there they consider a long cylinder of length L with inside radius R1 and outside radius R2 as shown in figure. Okay, this is the cylinder with length L1, inside radius R1 and outside radius R2 we are going to get. Then here let the T1 and T2 be the corresponding temperatures at R1 and R2. The inside and outside temperatures T1 and T2 have considered. As the length of the cylinder is very large compared to its radius. Okay, the length of the cylinder is large compared to its radius. Therefore, it is a long pipe. For it is assumed that for that cylinder, okay, there is a heat transfer takes place along the radius only, not along the length. Only one dimensional, one direction heat transfer takes place. That is a one-dimensional heat transfer. Then now we'll consider for the three-dimensional heat conduction equation in cylindrical coordinate is given by dou square T by dou R square plus of 1 by R dou T by dou R plus of 1 by R square dou square T by dou pi square plus of dou square T by dou Z square is equal to Q by K, that is equal to 1 by alpha dou T by dou T. And for one-dimensional steady state without internal heat generation, this three-dimensional heat conduction equation will be reduced to this term, that is a dou square T by d R square plus of 1 by R dt by dr is equal to 0, because only in the radius, along the radius in the radial direction, heat transfer takes place in only one direction. The boundary conditions are at R is equal to R1, T of R is equal to T1, at R is equal to R2, T of R is equal to T2. That is, at the inside surface it is subjected to temperature T1, outside surface it is subjected to a temperature T2. Then this equation 2 whatever is there, that equation can be rearranged as R d square T by dr square plus of dt by dr, that is equal to 0, and d by, this can be rewritten as, this is the differential equation, that differential equation in this term that can be written according to the mathematics as a d by dr of R dt by dr is equal to 0. Then equation 4 is a one-dimensional steady state without internal heat generation general equation, and this to find the heat conduction equation we have to integrate twice. Okay, integrating twice, that's the first, after the first integration R dt by dr is equal to C1, or we can write dt by dr is equal to C1 by R. This is sending this R to other side, the C1 by R we are going to get. T of R is equal to C1 ln R plus of C2. Again, after integrating this one, C1 ln R plus of C2 we are going to get. Then where C1 and C2 are the constants of integration. Then applying the boundary conditions to this equation 5, we are going to get T is equal to T1 when R is equal to R1. T1 is equal to C1 ln R1 plus of C2. T2 is equal to C1 ln R2 plus of C2 we are going to get. And here subtracting this equation 6 from the 7. Then T2 minus of T1 is equal to C1 ln R2 minus of R1, and this C2 get cancels. Then C1 can be written as T2 minus T1 by ln R2 minus of ln R1, that is a ln R2 by R1 we can write. Then substituting value of C1, okay, the substituting the value of C1 in any one of the equation, 6 or 7, we are going to get the C2. Then therefore C2 is equal to T in the first equation, T1 minus of the C1 ln R1. The C1 term is a T2 minus T1 by ln R2 by R1 into ln R1 we are going to get. Okay, then substituting these values of C1 and C2 in equation 5, okay, where the temperature distribution is there, T of R is equal to this T2 minus T1 by ln R2 by R1 into ln R1 plus of T1 minus of T2 minus T1 ln R1 by ln R2 by R1. then T of R, T2 minus T1 by ln R2 by R1, then this whatever is there. Okay, here T2 minus T1 by ln R2 by R1, from these two terms if you take the common, then ln R minus ln R1 remains, ln R minus ln R1 remains, that can be written as ln R by R1 plus of this T1, plus of this T1 we are going to get. Then this is the temperature distribution equation. The T of R is equal to T2 minus T1 by ln R2 by R1 to ln R by R1 plus of T1. This is the temperature distribution through the cylinder for one direction. Then the rate of heat flow through the cylinder for one of the surfaces from the surfaces of area A is given by Fourier law of conduction. Then Q is equal to minus K dt by dr at R is equal to R1. Then this one whatever is there here, dt by dr at R is equal to R1, that is C1 by R is there, that also we can substitute, or this temperature distribution, that is the T of R, we can substitute and differentiate with respect to R. Instead of taking that one C1 by R, will take the C1 value C1 by R at R is equal to R1, this is the C1 by R1, then the C1 value is T2 minus T1 by ln R2 by R1 into 1 by R1 we are going to get. Here then area minus K whatever is there. Okay, in this area whatever is there, in the radial direction area is this inside surface area. That inside surface area is a 2 pi R1L. 2 pi R1L. Okay, this R1 gets cancels, only 2K into 2 pi L, pi L remains. Then we can write Q is equal to 2 pi KL T1 minus T2 by ln R2 by R1. Okay, then 2 pi KL T1 minus T2 by ln R2 by R1. Rearranging this equation. Okay, if you this is the heat conduction equation for the cylinders. If you rearrange this equation, we are going to get Q is equal to T1 minus T2 by ln R2 by R1 by 2 pi KL. Okay, this is thermal resistance. Then thermal resistance according to that one we can write Q is equal to T1 minus T2 by R, where R is equal to ln R2 by R1 by 2 pi KL. The above equation can also be written as R is equal to R2 minus R1 ln 2 pi R2L by 2 pi R1L, R2 minus R1 into 2 pi KL. All these terms in terms of the mean whatever the area is there by taking that one. Okay, with this I'll conclude here only, and for the sphere and also for the this composite systems I'll continue in the next class. Thank you.